Good morning, everyone. We're going to continue into chapter 10 this morning. Last time we were talking about from Avogadro's finding of the volume of a gas at STP at 0 degrees C and 1 atm. We can use that to determine the ideal gas constant R. So we were looking at this constant R and saying, how can we solve for it? Well, if we know pressure, volume, N, and T, then we can solve for R. And so we're solving for R here. And then we come up with a variety of values. The primary one that we're going to use is the 0.08206 liter atmospheres per mole Kelvin value of R. Now, if you change and convert the pressure, so standard pressure in torr would be 760 torr, and you can resolve and you come up with the liter torr per mole Kelvin value. I've never actually used this value in a problem, because what I would probably do, if I have a problem, let's say where I need to relate pressure, volume, N and T, and I'm trying to say, let's say I'm trying to solve for pressure by taking nRT and dividing by volume. If I know 3 of the 4 variables in the equation, I can solve for the 4th. Let's say I'm trying to solve for the pressure and I want it in, if I'm trying to get the pressure in torr, I would probably just use the 0.08206 value, get the pressure in atm, and then convert the pressure to torr afterwards. So this is pretty much the one value I'm going to use for almost every problem until we get to a point where we're trying to calculate velocities in a couple of sections from now. So when I get to a point later where I'm trying to calculate something in SI units, I'm then going to use one of these 2 numbers here. These 2 values here are what I call the SI unit version. Because if you think of the SI unit of pressure, it's the Pascal, not the ATM. Even though ATM is more commonly used in pressure, at least in the early part of chapter 10, we're going to use ATM more than Pascal. It's Pascal that's the SI unit. And then later, when I want to calculate a velocity in meters per second, which is an SI unit for velocity, I'm going to want to use the SI units of R. So we'll come back to the 8.314. We'll actually derive it later to see where it actually comes from. Right now, I think it'd be kind of off topic to show you that derivation. But for now, what we want to get into is a couple applications of the ideal gas law, where one application is just relating densities and molar masses to the equation. So we can make use of the fact that moles, N, is the mass of a substance, the grams, and then divided by the grams per mole. So if we take mass, M, divided by molar mass, then we get the moles. So we get moles N from taking mass divided by molar mass. And so if I'm looking at my ideal gas equation, I can take PV is equal to nRT and rewrite that as M over molar mass, RT. And so then I have a situation where if I know the mass of a sample, the pressure of a sample, the volume of a sample, and the temperature of a sample, I can solve for the molar mass of the gas. So if you look at the equation, PV is equal to M over molar mass RT, then we have 1, 2, 3, 4, 5 variables. So then if I know 4 of those variables, I can solve for the 5th. And so that's a way where if you know, and we'll see a problem of this in a few slides, but if you know the mass that's in a container of a certain volume at a certain temperature, and you can measure the pressure of the container, we can then calculate the molar mass of the gas. We can also rearrange the equation to relate densities. And so if I have the equation PV is equal to M over molar mass RT, and I want to solve for density, density is mass over volume. So if I want to relate the mass over volume, then I can divide both sides by volume. So I can write pressure times molar mass. Let's get molar mass to the left side of the equation. M over V, dividing both sides by volume, and then times RT. And then I can divide both sides by RT, and then have pressure times molar mass over RT is equal to M over V, where of course this is equal to our density. So we can write that density is equal to pressure times molar mass over the gas constant times temperature. So a couple of different equations that can relate density to the pressure, molar mass, and temperature of a gas sample. It seems as if the volume and the mass of the sample have dropped out, but that's just because their ratio is the density. And so density is the mass over volume ratio. And then of course we can use an equation like this here to solve for the molar mass of a sample. So let's look at a couple of equations or a couple of problems that relate some different applications of the ideal gas law. And so let's look at the first question. So what is the pressure of a certain quantity of CH4 in a certain liter vessel at 23 degrees C? And the options I think we would have for this first problem here is we could either just convert this to moles right off the bat and then plug into PV is equal to nRT. So I think the first problem, we might just say, well, convert the number of moles in the 7.50 gram sample of CH4. So the molar mass of CH4 is 1.008 for the hydrogen times 4 plus 12.01. So it's 16.04 grams per mole. And so that gives us a value that's a little less than half a mole. So 0.468 moles. So I could just solve into PV is equal to nRT, rearrange for pressure, divide both sides by volume to solve for pressure. And so I can plug in my number of moles. I, of course, could have went m over molar mass RT divided by V as well. So I could have just left this equation with m over molar mass, but I've gone ahead and solved for the moles right off the bat. So I'm going to plug in 0.468 moles times the gas constant. I think if you just routinely use the gas constant, the 4 sig figs, then you won't have a rounding error later. So I usually use 4 digits here just to kind of make sure I'm not prematurely rounding. A lot of people round it to 3 sig figs. That's probably okay. I doubt on a test that you're going to get an answer wrong if you use 0.0821. But the key would be, once you do a couple of problems, hopefully you've memorized this number. Of course, it's on test. If you need to look up the gas constant or Avogadro's number, these constants that we use a lot, that's fine. But I think doing enough problems where you memorize some of these key details makes sense. 23 degrees C, we just have to go to Kelvin, of course. We see Kelvin in the unit here helps us. But so we want to take 23 plus 273 to convert to Kelvin, and then divide by, and I could have went 273.15, but I would have rounded that to the ones placeholder. So I kind of dropped the 0.15 just because I'm not going to need the 0.15. They're going to round off on our rounding on the sig figs here anyways. And so then I'm going to divide by the volume of the container, 2.50 liters. So moles times the gas constant times 296 Kelvin, divide by 2.5 liters. I get 4.54 ATM. Or let's even think about the units for just one moment, just to make sure we're seeing our Kelvin cancel, our moles cancel, and our volume cancel, and we're only left with atmospheres as our unit here. And so the question did say calculate the pressure in ATM and in torr. Now, one option for the torr would be if you had the torr liter per mole Kelvin, you could go resolve this equation and plug in your different unit of R here. But of course, we can just apply that 1 ATM is 760 torr, or exactly 760 torr. So multiplying that pressure by 760, I get 3450 torr. So if you want a pressure value in a non-ATM unit, just use the ATM unit for your gas constant, then just apply your pressure conversion afterwards. Now, for the density, I think there's two approaches here. The first approach for calculating the density is to use the equation that we had derived or gotten to, pressure times molar mass divided by RT. And so our pressure is 4.54 ATM. Our molar mass is 16.04 grams per mole. And then dividing by the gas constant, and then times 296 Kelvin. So the density of this gas is in units, boiling down to the unit grams per liter. I've mentioned a couple times, I know it's easy to skip writing units, but especially in an equation like this, if we forget our units, we may not know where the unit's supposed to be grams per liter, grams per milliliter, grams per what. Here, just showing the units, we clearly see we get grams per liter by taking the math here, 4.54 times 16.04, divide by 0.08206 and 296. So I get 3.00 grams per liter as the density. So that's a pretty low density, right? Because like water's 1 gram per milliliter, which would be 1,000 grams per liter. And so this is obviously a pretty low density compared to, say, that of a liquid. But now, were you thinking that there's an easier approach? Was anybody there saying, well, there's a much easier way to calculate density, and that's just mass over volume? And we could have taken, we know that there's 7.50 grams in the container from the original amount of mass that was in the container, and then we knew the volume of the container was 2.50 liters. And if you notice, that also works out to be 3.00 grams per liter. So 2 ways to think of density here. Either you can just go back to mass over volume, and that's one way to calculate it, or we can apply the equation, like once we know the pressure, we can then think pressure molar mass over RT. So they both work, they get the same value. Now, I think a tricky question would be, how does this gas get to STP? You know, like if we have a container, it could be a gas cylinder. So imagine you have a cylinder that contains, you know, this much CH4 in it, and it has this particular pressure of about, you know, 4.5 times standard pressure. How, like, for it to reach STP, the pressure would have to lower, so we're gonna have to probably expand the gas. The temperature is going to have to change, it's going to have to lower, which is going to lead to kind of a compression of the gas. So we can think to get to 1 atm expansion, to lower the temperature, kind of back contracts a little bit. So we're probably gonna think that if this sample is going to be at STP, we're gonna have to change some of the characteristics of the gas. Like if we're going to maintain the same volume, then we have to get rid of some gas, would be another way. So if we want to keep the same container, if we say I have this container that has 4.5 atm and it's 296 Kelvin, if I want the pressure to be and temperature to be at STP, then I'm gonna have to like lose some gas. So another way to get to STP would be to keep the same volume container, the same volume of the container, but then just lose some of the CH4. So then we have less mass in the container, so that we go down to having the right mass to volume that would match having a pressure of 0 degrees C in 1 atm. And so when we're calculating the density here, so the density the gas would have is presumably going to be lower, because we're gonna have to lose, like if we're keeping the same volume container, again, if we wanna lower the temperature and lower the pressure, the only way to do that by keeping volume the same would be to lose N. We have to get rid of some of the gas in the container. And so the density is only related to so the density of this gas under the STP conditions, either through the expansion of the gas into a larger volume or getting rid of some of the gas from the container, is easily calculated by taking the pressure that it would have 1 atm. The molar mass is still the same, 16.04, it's still CH4, so the molar mass is the same. And the gas constant and again, remember STP is 0 degrees C, not 298, so that's 273 Kelvin. If we want to be technical, STP is precisely 0 degrees C. So here we can use this 273.15, and it makes sense to use those extra units here. So we go 1 atm, and it's precisely 1 atm. So I'm looking at these two values here. Let me change color. Like this is an exact value, and this is an exact value, because those are the idea that at STP is precisely 1 atm and precisely at exactly 0 degrees C. So we go 1 times 16.04, divide by 0.08206, and then divide by 273.15. And so now I get a lower density. It's 0.716. We can actually give one more placeholder, 7156 grams per liter. So the 1 and the temperature, those are not causing us to round here to like 1 sig fig or anything like that. So this is exactly or precisely 1 atm, 0 degrees C. So that's showing us that the density has to lower if it were to reach STP, to reach a pressure of 1 atm at 0 degrees C. Okay, so that's a couple applications. Other applications are generating gases from chemical reactions, so we can look at problems that also relate to that kind of an idea. So another application of gas laws is that we can generate from, say, a solid. Here we have sodium N3, that by name is sodium azide. Azide's not an ion from our nomenclature that we had memorized, but this is an interesting ion called the azide ion. You might see it a little bit in OChem if you take 25, 10, and 20. But anyways, a compound NaN3 is a unstable compound that if you apply a spark to this compound, the delta is usually meant to imply just hold a match to it for a second and it will quickly undergo the reaction where it converts into sodium and N2. If you recall, this would be a decomposition reaction from chapter 3. So it undergoes that decomposition reaction. But one of the products is a gas. So if you notice, the other two substances, like the reactant and the other product, are solids. So the only gas being formed here is N2. And so this is a reaction that can be performed if you imagine having like a balloon that's deflated and you have some sodium N3 or NaN3 that can rapidly decompose. So you apply a spark to the sample and all of a sudden your balloon can grow. This is actually a reaction that used to be used a lot in airbags and cars. So it used to be the mechanism by which an airbag would be filled would be that there'd be a little pack of NaN3 that's just waiting for a collision. And when a collision happened, it would lead to a shock-sensitive compound igniting that would ignite the sample, it would burn, and then produce the N2 to fill the airbag. It's actually not used so much anymore because a lot of times sodium, if you recall, we put sodium into water, not a fun reaction. So a lot of times the N2 fills the airbag and sodium comes along for the ride and it ends up melting the airbag, burning the person that's in contact with the airbag. So it's really not the most useful reaction anymore these days. Airbags usually just have a CO2 pack that's pressurized and is waiting to fill the airbag upon collision. But still the question here could be, how many grams of this compound of the reactant do we need there initially to be present in order for us to be able to fill an airbag to 50 liters, 50.0 liters, if the pressure of the airbag is going to be 1.25 atm and it's going to be at 22 degrees C, 22.0 degrees C, according to this reaction. So what we would want to figure out is from PV is equal to nRT, of gas. So obviously this is about the N2. So we might rewrite this. This is the moles of N2 that would be in the airbag times RT. And so we want to figure out first, how many moles of N2 does there need to be in this airbag that's filled to that particular pressure and volume? So we have N of N2, the moles of N2 would be equal to PV over RT. So just rearranging for solving for N, dividing both sides by RT. And so we want the airbag to be filled to 1.25 atm. It has to have a volume, or has a volume of 50 liters, and our gas constant. And then it's at 22 degrees C, which is 295, 22.0 degrees C. So I'm going to keep the 1.5 along for the ride because I have at least that fourth digit significant there. And so if I solve for moles, so 1.25 times 50, divide by 0.08206 and 295.15. So I get that there has to be 2.58 moles of N2 inside of that airbag in order for it to have a volume of 50 liters at a pressure of 1.25 atm at this temperature. So again, just double checking our units, atm cancels, liter cancels, Kelvin cancels, and we're getting 1 over moles in the denominator, flipping up to moles in our product. So the key is that this is the moles of gas. So this equation here, of course, relates to the moles of the gas that are produced in the reaction. And so in order to produce that many moles of N2, do you see how this then relates back to a stoichiometry problem? So in order for us to get 2.58 moles here out of this reaction, I then have to think by stoichiometry, how much NaN3 did I have to start with? So when the question is how many grams of NaN3 are required, hopefully hopefully you're thinking this just kind of goes back to chapter 3 of saying if we need to produce 2.58 grams of a product, or excuse me, 2.58 moles of a product of N2, then I just need to use my coefficients that for every 3 moles of N2 that were produced into that airbag meant that 2 moles of NaN3 had to have decomposed to produce it. So I'm just looking at my 2 coefficients here. For every 3 moles of N2 that are formed, 2 moles of NaN3 had to have decomposed. And then I just need to use the molar mass of NaN3, which is 14.01 times 3 plus 23.00 for sodium. It gives me a mass of 65.03. Grams. So I get 112 grams. So if you start with the solid being present, you then allow it to decompose through its reaction taking place. You could double check if you wanted 112 grams. Let's convert that to moles real quick. So that's divided by 65.03. So that's 1.72 moles of our reactant. And then for every 2 moles of that decomposes, we get 3 moles of NaN3, 2.58 moles. And so then we're just thinking, well, what would the pressure, volume, temperature of that quantity be? 50 liters, 1.25 ATM. Okay, so 112 grams of the reactants required to decompose. So this is how we can relate a chemical reaction taking place to give us the gas that's being formed in order to actually fill something like an airbag. Okay, so let's take a look at having more than one gas present in a mixture. We talked at the start of chapter 10 here, we were talking last time about how air is an example, a very common example of a mixture of gases. We have 78% by volume N2, 21% O2, and then a little over 1% is everything else, from things like argon being most of everything else, but then like water vapor, CO2, and other substances in the atmosphere. And so the total pressure of a gas mixture is just the sum of the individual partial pressures. So if 2 gases are present that aren't reacting, so we imagine like N2 and O2, they don't react together. If they bump into each other, they just collide and go about their day, and they don't do a chemical reaction together, which is good because it'd be hard to understand how we have N2 and O2 present in the atmosphere if they react together readily. But we have 2 gases in a container that aren't reacting together, then the total pressure of the gases is just equal to the sum of the pressures that each gas would exert if the other wasn't there. So if you look at the atmosphere as an example, the total pressure, atmospheric pressure is about 1 atm, and if 78% is N2, then the partial pressure of N2 is about 0.78 atm. The partial pressure of O2 is about 21% O2, so it's about 0.21 atm of O2. The partial pressure of argon, which is about 1% of the atmosphere, so the partial pressure of argon is about 0.01 atm. You take all these, you sum them up, you get the total pressure being your 1.00 atm. So you add all the individual partial pressures of the components of the atmosphere, that's what's contributing to atmospheric pressure. And so to say crude examples, if you want to calculate the total pressure of any gas mixture, you just take the sum of the partial pressures of each of the components of the gas mixture. So if you have 3 components, you just simply add up the 3 components. If you have a 2-component mixture, you just add up the 2 individual partial pressures. And we'll see an example on the next slide of how we can calculate some individual partial pressures and a total pressure. Okay, so let's look at mole fraction as well as a unit, and we're almost using that on the previous slide too, so let me in here a little bit. Okay, so mole fraction. So what is mole fraction? How does it relate to total pressure? So if I take the ratio of the partial pressure of one component to the total pressure, I could then think how I can just write that, PV, that's not PV, it's RV. PV is equal to nRT. So if I have pressure 1, so the pressure of component 1 relate to the moles of component 1, And so P1 would be nRT divided by V. And so you see partial pressure 1, the partial pressure of component 1 would equal the moles of component 1 times RT divided by V. And then the total pressure of the container would be the total number of moles times RT divided by V. But because if you have a gas mixture, if you have two components in a gas mixture, they're at the same temperature and volume because they're in the same container. So T and V of the two gases have to be the same as each other, because to be in the same container means, of course, they have the same total volume, and then they have the same total temperature because they're bumping into each other. They have the same temperature as each other. And so, of course, the gas constant's a constant and is the same as well. So that leads RT and V to canceling out. So the ratio of the moles of the two gases, the N1 compared to the N total, is just N1 over NT is equal to P1 over P total. This here, the moles of one compared to the moles of the total, that's what we mean by mole fraction. So mole fraction takes symbol X. So X is mole fraction. Mole fraction has a symbol X here. So the mole fraction of 1 is the moles of 1 divided by the moles of the total. So it's just the fraction of the moles that are 1. And we call that the mole fraction. And so then you can see that if N1 over NT is equal to X1, then X1 would be equal to P1 over P total, so that you can write that the partial pressure of component 1 is equal to the mole fraction of component 1 times the total pressure. So if you just rearrange this equation here, X1 is equal to P1 over P total, just multiply both sides by P total to get mole fraction 1 times the total pressure is equal to the partial pressure of component 1. Sounds like a lot, but what we're just saying is that if you multiply the total pressure by the mole ratio of a component, you get the partial pressure of that component. So X1 is the moles of component or compound 1 compared to the total number of moles, that's N1 over N total. So partial pressure of 1 is mole fraction of 1 times the total pressure. So it just is a couple formulas that help us relate mole fraction to total pressure to the individual partial pressures. And just again, remember that total pressure is just the sum of all the individual partial pressures. So if you have multiple components, you're just adding them all up to get the total pressure. Now this also leads to another idea, which is if you look at the equation PV is equal to nRT, that if N is, if pressure and volume are proportional to each other, then the ratio of the two kind of go hand in hand. So if N goes up, the pressure goes up. And so if you know a mole percentage, then that's going to tell you the pressure percentage of the mixture. And it also tells you the volume percentage of the mixture. So if you go back a couple of moments where I said air has a percent by volume of 0.21%, 21% oxygen, 78% O2 by volume, that's also the same percentages by moles because V and N are related to each other. The volume percentage is the same as the mole percentage, the same as the pressure percentage. And so whenever I'm saying something 78% by volume N2, then it would be, so 78% N2 by volume would also be the same as the percent by mole, and the same as the percent by pressure. So 78% of the total pressure is N2, 78% of the total moles of air are N2, 78% of the volume of air is N2, is the idea here. Now the only one that wouldn't apply is by mass. And so because if you think of the percent by mass, then that doesn't hold true because each component of the atmosphere could have its own individual molar mass. And so the mass is not in this equation here for each of the components. So we don't see M in this equation here. So the percent by mass, you can't say 78% of the mass of the atmosphere has to be N2. Only that 78% of the moles, 78% of the volume, 78% of the pressure is due to N2. So let's look at a problem here that relates individual partial pressures to hopefully a relatively straightforward problem. So what is the total pressure of a mixture that has 5 grams of helium, 5 grams of oxygen in a particular vessel, 15-liter vessel at 298 Kelvin? And so a couple of ways we can think of solving this problem would be, I think, I'll show you two different ways. Let's look at way one, I think would be that our total pressure should be equal to the partial pressure of helium plus the partial pressure of O2. And then we could calculate those two individual partial pressures as if the other wasn't there. So the partial pressure of helium would be equal to nRT divided by V, but for helium. Let me save a little room here to write N of helium times RT divided by V. And then the pressure of O2 would be, the pressure of O2 would be the moles of O2 times RT divided by V. So my total pressure would be equal to 5.00 grams of helium times 4.003 grams per mole of helium. I think it's 4.003. Yeah, we'll say 4.003 grams per mole, and then times R. And then times the temperature, 298 Kelvin. And then divide by 15 liters. And if you were thinking we could have done some factoring here, we probably could have been smarter with our math and not have to like do the exact same math over here. But it's easy enough, I think, to also then say, well, it's for O2, it's 5 grams of O2, 32 grams per mole for O2. And then times RT, the same R and the same temperature, but I'll just write RT and then divide by 15 liters. So 5 divided by 4.003 times our gas constant times 298 divided by 15. This is just the pressure of the helium. And then plus that from oxygen, 5 divided by 32 times the same gas constant times 298 dividing by 15 liters. Now, having the same mass of O2, because O2 is more massive, gives you fewer particles, which gives you a lower pressure. So we get a lower pressure for oxygen here. The partial pressure of oxygen is 0.255. So our total pressure, we equal those two values added together. Of course, we only have 3 sig figs on each of them. Gives me 2.29 ATM. So this solution here, like this, there may be a shorter way mathematically. I'll show you a second way to solve for the total pressure. But I like this way because it has us calculate the individual pressure of helium. We can see what it is. So helium's pressure, if we didn't have O2 in the container, would have been 2.04 ATM. If we only had oxygen in this container, if we only had a container with 5 grams of oxygen in this particular container, its pressure would be 0.255 ATM. If we have the two present together, we just sum up the two individual partial pressures, get to 2.29 ATM. Now, a second approach would have been to solve this problem. So if we say, you may have been sitting there thinking that there's a faster way to solve this problem, and that is the total pressure would just relate to the total number of moles times RT divided by V. So we could calculate the total number of moles. So I could have looked at the 5 grams of helium up here and said, well, 5 grams divided by 4.003 grams per mole, that's going to be about 1.25 or 1.2 grams. What is that? 4.003. It's 1.249 moles of helium, and the 5 grams of O2, 32 grams per mole. And so that'll give us a lower number of moles, but that's 0.15625. So the NT, adding these together, would be 1.405, Just carrying one extra digit here for number of moles. And so you may have been looking at this problem saying, well, I'll just calculate the sum of the two moles. If you were thinking that this may have been a faster way, more efficient way to solve the problem, I think you would probably be onto something. That we could have just put this here as our total number of moles times our T divided by 15 liters. So if I take that number of moles times the gas constant times 298 divided by 15, I get 2.29 ATM. So two approaches here that you may have been thinking were valid ways to solve the problem. I like the first approach, at least to show you guys that we can calculate the two individual partial pressures and just add them up. But we could also just apply the total moles are related to the total pressure from the ideal gas law and solve accordingly. The key on an exam, of course, would be choosing a way that gets you to the correct answer. If one way takes you a little bit longer, takes you an extra step or two, but you get the right answer, I say that's a win. If you cut a step out, but you're not sure it's the right approach, that's probably one that's a little bit iffy for a test. So if you're thinking on a test, should I try a shortcut or should I try the long way that I know will work? I would say just probably do the longer way that will work just to make sure you get the answer right. Okay, so a lab technique, and we used to do this, I don't think they do this anymore in the lab, and occasionally in some semesters we did this in 1220. I don't think you start 1220 with this anymore, but a couple of years ago I think we used to start 1220 off with doing an experiment like this, which is where you take a boiling water bath and you take a flask. The first part of the experiment is actually trying to figure out the volume of a flask that kind of has a somewhat random volume to it. So you fill the flask with like water, you then drain the water into like a graduated cylinder, you figure out the mass of water to relate the volume of your container. So usually the first step of this problem is figuring out what's the volume of this vessel. And the problem here that's worked out for us, that it's 355.3 cubic centimeters, which of course would be 3,553 liters, because that would be just milliliters and cubic centimeters are the same. So in terms of the volume in liters, it would be 0.3553 liters. And then what we would do with this experiment is we could put a liquid, a substance that's a liquid at room temperature that we can then submerge in a boiling water bath that's going to be high enough temperature to vaporize the compound. So as long as the compound, so what we're going to do is we're going to take a sample of liquid that can be vaporized in boiling water to determine the molar mass of the gas from the data that we have shown here. So what you do is you start with a nice clean dry flask. You start with this flask here that's clean and dry before you start the experiment, so you figure out its mass. You then fill the bulb with some liquid. You put like 5 mils of your liquid into the flask. You put a little bit more liquid than you need to vaporize into the flask. And so we're gonna put about 5 grams or so of liquid into that flask, get the mass of the bulb with that liquid. We're gonna then submerge that flask in a boiling water bath for long enough for that sample to fully vaporize. So we're gonna have this flask submerged in water just so that the tip of the flask is open and that the gas that vaporizes can escape the flask. And so then the idea is that all of the air inside the flask should be replaced by the compound's vapors as it vaporizes. So if you think of the flask when you start, you have liquid and air. And then as that compound vaporizes and it forms a gas, it should force the air out of the container. So the entire bulb should be filled up with your vaporized sample as gas vapors at the temperature of boiling water. So we're gonna have this bath here at 100 degrees C. And so the temperature inside the flask, of course, would be 100 degrees C. And so then we have to measure atmospheric pressure because the pressure inside the flask is atmospheric pressure because it's open to the atmosphere. So the pressure inside the flask is atmospheric pressure, which for whatever reason the day this experiment was done or this fake data was being calculated was 771.5 millimeters of mercury. So a little bit over standard atmospheric pressure of 760 millimeters of mercury. And I'm kind of showing here that if you use a barometer, you would probably measure it in millimeters of mercury. So it'd be very ordinary. If you were measuring a room pressure, it would probably come out in millimeters of mercury. I'm going to go ahead and just take this number right off the bat, 771.5, and then divide it by 760, and that would be 1.015 ATM. So I'm going to convert that to ATM right off the bat. And I think the only reason we're seeing in millimeters of mercury is if you were to do this experiment, it'd be very ordinary that you would have read the pressure off a column of mercury, so that would be your usual unit. So let's go back to how we relate pressure to molar mass, and then also then relate to the last value here that really matters, the mass of the bulb. So what you do is you vaporize this liquid sample until you look inside the flask and you see all the liquid is gone. And so you're gonna vaporize that liquid inside of the flask until you can't see any traces of droplets of water left, because at that point, all the sample is vaporized into its gaseous vapors. We've replaced all the water, or all the air inside the flask with the vapors of that compound. So then we can take the flask out of the water bath and then dry it off and then let it cool down. And so as the flask cools down, you then start to see a liquid emerge, because you have the vapor, the gaseous vapors of your compound that were hot cooling back to the liquid phase. So you start to see some liquid emerge back into your flask, but not as much as there was before. So you get a mass, you take a mass of the flask once it's the experiment's been finished. So you vaporize the sample, you've noticed by your eyes that all this liquid has vaporized, and so then you allow the vapors to condense. It's telling you how much vapors were in the flask that recondense back into the liquid phase. And so this is a long-winded problem to say we can relate pressure volume to mass over molar mass times RT. And so we've just set up a problem that you can do in the lab where the pressure here is your atmospheric pressure, the volume here is your container volume, the temperature here was at 100 degrees C, which is 373 Kelvin, and the mass here is the difference between your empty container and the post-vaporization value. So this mass here we don't need for the problem. Like the 116, that number's extraneous for the problem, because just imagine we had to put excess liquid into the flask, and then the key value is once you vaporize all that liquid and it recondenses, the number that matters is the 112.46, but not that number in and of itself, but that minus the mass of the empty flask, 111.34. And so we have 1.12 grams of compound that was in the flask at 100 degrees C, is the implication. So that's the mass of the compound that was vaporized inside the flask at 100 degrees C. And so what we can do is we can solve for molar mass from this data. So we can take our molar mass over to the left side of the equation, then have that equal to the, let's put an arrow here because I'm rearranging the equation. So multiply molar mass over to this side of the equation, then divide by PV. So we have M times RT, divide by PV. So molar mass is equal to mass times RT, divide by the pressure volume. And so the mass of the sample, 1.12 grams. I'm just going to write R, it's our usual gas constant. RT is 373 Kelvin. And then the pressure is atmospheric pressure, but in ATM. And then the volume of the container is the value, and the reason why I converted to liters was I need this in liters to cancel into my gas constant. Let me actually go ahead and write it, just to show the units here canceling. Our Kelvin cancels, our ATM cancels, liter cancels. The only value not canceling is grams and then per mole. So the only units not canceling in the gas constant and the units for mass are the grams per mole. So I go 1.12 times the gas constant, 0.08206, times 373 Kelvin, because that was the temperature at which we had the sample vaporized into a gas, the boiling point of water in Kelvin, divide by the pressure, 1.015 ATM, and then divide by 0.3553 liters. So I get that the molar mass would be 95.06 grams per mole. So very long-winded problem, and you'll see some examples of this, because the examples usually say, oh, a certain compound at this temperature had this mass. Yes?
I'm confused how we got the mass of the compound to be 1.12 grams when what's given is 112.46 grams.
Oh, yeah, so that's the mass of the entire bulb plus the liquefied compound. So when you do the experiment, you have like your bulb that's empty, you add some liquid, you add an excess of liquid, you then vaporize most of the liquid out of the container, but then, yeah, so it's the bulb plus the compound. So you're just subtracting the clean bulb from the 112.46. Okay, so this could be like the H2SO4 happens to have, like sulfuric acid happens to have this molar mass. So maybe this is sulfuric acid, I don't know for sure. But this could be a compound of something like that. And so this experiment here is an experiment that you can do in the lab to determine molar masses of gases. And so the idea here is you just, the key details you need to know is what is the mass of the compound, what is the volume of the container, what's the pressure of the container, and then what is the actual gas, or not what is the actual gas, how much of the mass of the gas is there, and then you can work out the molar mass. So the key here is if you go to this equation, PV is equal to M over molar mass times RT, we have 1, 2, 3, 4, 5 variables. So as long as you know 4 of the variables, you can solve for the 5th. Okay, so let's get into some of the discussion of how gases behave. There's a set of postulates called the kinetic molecular theory of gases that will help us try to understand how gases behave in a gas container. And so gases are in random motion is the first thought, is that a gas always have particles that are moving around the container. The particles are never still in a gas mixture. So the particles are always bouncing around the container. A gas has a low density, so the gas is not occupying much of the volume of the container. So we are assuming that gases have a negligible volume, meaning they're not occupying much of the space of the container. And then they have minimal or no attractive forces with each other. So if we're thinking of these two compounds, if they bump into each other, they're not sticky. They're not really sticking together. They're going to just deflect off each other like billiard balls. And so that they don't experience attractive forces. The gas mixture itself has to have a constant kinetic energy, meaning if you summed up the kinetic energy of each of the particles at any moment of time, where you could think kinetic energies is 1/2 mv squared. So if you imagine each of the particles at any moment in time has some velocity, and then each of the particles, you know their mass. You can work out the mass of each individual particle. And you can imagine for every particle in a mixture calculating its kinetic energy and summing up the kinetic energy. Then you could imagine if you then a few minutes later do the same process again, it would take you a long time, right? Because there's a lot of particles in a container. But what the thing that might happen is a fast particle might bump into a slow particle, and then the fast particle becomes slower, the slow particle becomes faster. So you have all these things colliding with each other, but the kinetic energy has to be conserved. That you can't have, at some moment in time, all the velocities turn out to be a lot higher than they were before. The average kinetic energy has to be constant with time. So the meaning there is that if there's going to be collision, so if molecules collide, energy has to be conserved. So we're not creating or destroying energy through collisions. So a fast particle hits a slow particle, they can exchange velocities where maybe one of them slows down, the other one becomes faster, but we're not creating or destroying energy with collisions. And so we have a constant average kinetic energy for a gas mixture, and then this average kinetic energy is related to temperature. So if we imagine changing the temperature of our gas mixture, what we're really toying with is that average kinetic energy. So if we increase or change the temperature of a gas mixture, then we're giving more energy to those particles so they can have a difference in kinetic energy. If we heat up a gas mixture, the particles will have more energy, they'll have more kinetic energy, they'll be moving around faster on average. If we imagine we go from temperature 1 to temperature 2, we increase the temperature, let's say, on average, all those kinetic energies will increase, but then once you hit that new temperature, at all moments, the average kinetic energy would be the same if we keep the same temperature. So at the same temperature, the sample has the same average kinetic energy. At a higher temperature, a higher average kinetic energy. At a lower temperature, we're slowing velocities down, we're going to a lower average kinetic energy. Now, if you think about it, a gas mixture is going to have a wide range of velocities. So if you look at a mole of helium, let's say, you have a container that has a mole of helium in it. It's going to be a pretty big container probably if you don't have a very high pressure of the helium. If you imagine at STP, it's 22 liters, so a pretty big container of helium. If you imagine the velocity distribution of all the helium atoms, you're going to have some fast ones, some slow ones. You're going to have a pretty wide range of velocities. We'll look at that range in a second. I thought it was the next slide. But let's look at this question first, and then we'll look at the range of velocities. So let's think about what happens when we compress a gas. So that's like you have a container with a piston and you're compressing down by pressing downward on the piston. And so when you're imagining going from a container that looks like this to then you're going to compress the gas down and have it then look something like this with the same number of particles in it, what then happens to those particles as they're bouncing around their container? Do the frequency of the collisions of the particles with the walls of the container increase? So if we compress a gas, do its particles hit the walls more often? And I think the answer would be yes. That's exactly what happens. If you take a volume that's this and then cut it in half, that all the collisions with the containers are doubling. You're going to have way more collisions with the walls of the container. And so this is another way of saying that the pressure should increase. So if the pressure increases, if you recall, pressure was defined by a force exerted onto a square area, that if you have a reduction in the volume, you're going to have more collisions, you're going to have more force being applied to the area just by reducing the volume and compressing the gas. So you're going to have an increased force hitting now a less square area, so the area that you're even hitting is becoming lower, and so that should give you the picture of a increased pressure inside your container. And so then let's look at, so statement 1 seems like it's a true statement. What about statement 2? The average velocity of the particles increases. So when I compress a gas, momentarily when I push the particles out of the way, they might for a moment of time like move faster just to kind of like get out of each other's way. But once they settle, the average goes back to what it was before. So the only thing that can change the average velocity of our particles is temperature. So if I want to increase temperature, then I can increase the average velocity of our gas particles, but I'm not changing the temperature when I compress a gas here. So I'm compressing the gas at constant temperature. And so because temperature is constant, the velocity of the particles has to be constant. So the average velocity of the particles has to remain the same. So the particles are still moving around with the same velocity, even though we've increased their pressure. So it gives you an idea that when you increase the pressure, you might be thinking, okay, I'm now making the particles move faster. No, the only thing that can make the particles move faster is changing their temperature. So only statement 1 holds true here. But what I was really hoping to look at was the actual distribution of these velocities. So when we look at the actual distribution of velocities, let's look at this slide. Let's look at B first. So B is showing us that for a gas, we're looking at a breakdown of what are the fraction of molecules that have a particular molecular speed. And so if you notice, we have some very slow particles, some very fast particles, but most of the particles are kind of somewhere in the middle. So we have a wide range of velocities for a gas mixture, but we have a description that is not a perfect parabola. So if you notice, the shape isn't a perfect parabola, but it's kind of like a weighted distribution where, and sometimes we call this a Boltzmann distribution, where you get a fast distribution first and then you get like a tail. And so when you have this tail here, it means your average is not going to be at the peak. Your most probable is the highest peak. So the most probable is the highest peak. The velocity that most of the particles have is our most probable velocity. So that's our most probable. And then we have the average, which is going to be higher. And then we have something called the root mean square velocity. The RMS velocity is the speed at which the particles have the average kinetic energy, which is kind of a mouthful. But there's like 3 different average type velocities that you can compare for a gas mixture. That is the most probable, the average, and then the root mean square, which this just then relates to the average kinetic energy point. So that's just the point, the velocity at which the half the particles have the lower kinetic energy than the average kinetic energy, then the particles have a greater kinetic energy than the average particle. So most probable, average, and root mean squared. The key is just seeing that it's because it's not a parabola, these are not centered on the same point. These each have a unique value. But if you go from 0 degrees C gas to 100 degrees C gas, notice at 100 degrees C, we shift all the velocities to be overall on average greater. So what temperature is doing is it's on average, we're increasing the velocity of our gas particles, which velocity, kinetic energy go hand in hand, 1/2 mv squared. If we increase the average velocity, we increase the average kinetic energy. So temperature is just a measure of average kinetic energy. So higher temperature, higher average kinetic energy, higher averages of velocities for our gas mixture, and then lower temperatures, lower average kinetic energy, lower velocities overall. Okay, we'll pick up from here on Wednesday, guys. Have a great day.